we're just going to kind of continue from last time, the last lecture that we did, and I'm just going to start with just a small recap of what was done in the previous lecture, just a small introduction. And this time we'll be talking about sequential games, and we'll also look at the Stackelberg model, and we'll look at games with imperfect information and information sets. We'll also look at the subgame perfect equilibrium.
No, I don't think you can cover all this.
Well, it's just a very small introduction to everything, so it's not going to take long. So just some examples and like a basic introduction to these. So most of these are from Professor Ben Pollack's lecture, like the Yale game theory lectures. So yeah, we'll just start with like a small recap of last time. So I hope you remember the payoff matrix from last time. So let's say we again consider like two players, 1 and 2 here, and we have a strategy C and D. Let C be like a cooperative, and D is a defect strategy. So we enter the payoffs here. So this is basically the payoff matrix, and these are the payoffs. So 2 is basically the payoff from player 1. So when player 1 basically selects cooperate strategy and player 2 is cooperate, right? C and C, so he gets a payoff of 2 and the second player gets a payoff of 2, right? So this is basically the simultaneous game from last time, where each player basically plays his move, simultaneously. So you don't know what the other player has done or whatever, right? So this is basically a classic example of what they call in game theory like a prisoner's dilemma, a problem where a prisoner basically tries to either cooperate with the other prisoner or defect with the other prisoner, right? So if you cooperate, let's say if you cooperate with the other prisoner, you get a payoff of 2 and he gets a payoff of 2. And if one cooperates and the other defects, right? The person who cooperates gets a payoff of -1, and the person who defects gets a payoff of 3, right? So this is how it was. Like we talked about this last time, and we also saw which was the dominant strategy here. So no matter let's say you're playing player 1, so no matter what the other person chooses, right? No matter whether player 2 chooses C or D, you end up in a better position when you choose defect. So do you get that? Like if player 1, right? If player 2 chooses C, right? You basically, by defecting, get a payoff of 3, and here you get a payoff of 0 when compared to the cooperate strategy. So defect is always the dominating strategy, and we also found from last time the Nash equilibrium to be 0, 0, which is basically a defect. So the Nash equilibrium is nothing but the optimal, the most, let's say the optimal solution for the game. So in this particular simultaneous game, the classic prisoner's dilemma, it was defect, defect, right? So this was what was we had talked about last time. So we'll now look at more sequential games. Here we looked at just one simultaneous game. You're given you're given 2 strategies. You just have to pick one strategy, right? And you don't know what the other player has picked. It's more like simultaneous. The choices are made simultaneous. But in sequential games, you pick. If you play 1, you pick first, and then player 2 picks second after observing your choice. So as time goes by, you pick your strategies. So you know what the other player has picked, and in due course of time. So let's try playing a small game here. So So let's say that you have okay, Sean, can you be player 1?
Yeah.
Can you be player 2?
Is there a 2?
No, there will be a 2.
Okay.
Okay, so basically you have like choices 0, 1 and 3, right? Okay, and basically dollars. Okay, so if you put $0 in, let's say you have a hat or something like that, if you put $0 in, right, you get back nothing. So it's basically the payoffs are like you put $0 in, right, your payoff is basically 0. Okay, and if you put $1 in, right, and if the same money is matched by pay, right, you get like a net profit of 1. Okay, so you totally get 2. Okay, and you get -1 if not. I mean, if he doesn't match. Okay, he can either take the money or he can like match the money, right? So, and if you put
take the money.
you can just take the money. I mean, so let's say he puts $1 in the hat, right? Let me come to you right after him.
Okay.
So you get a net. This is net. So 3 and -3. Okay, this is your payoff. So if you put 1 in the hat, you get +1 if he matches the amount, and -1 if he just takes the money. Okay, so you get a +3 and he gets a -3. Okay, so pay, right? I mean, you get a net of 1.5, right? If you match the amount. Okay, this is for 1. Okay.
So if they put $1, then he gets one.
Yeah, he gets 1.5. You get 1.
Who pay for that 1.5? The total.
No, I'll pay. I mean,
Okay.
like whoever. It's just it's outside. It's outside. Okay. And 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 you can obviously take the money and run away. You know that, right? And you get if you match. I mean, this is for 3. Okay. So you get a net of 2 if you match 3.
Can I put 0?
Huh?
Can I put 0 as well?
No, I mean, if he doesn't put anything, there's no game basically, right? I mean, you also. It's just when he puts some money, it comes to you.
So does it? So
You get a pay. Okay, so
does he lose?
which one?
Does Bailey lose at any point, or just?
No,
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 he always gets.
no. It's not like it will be more evident when it's not a thing of who wins or who loses. This is more like well, this is. Let me explain it a bit more in detail. But these are how the payoffs are. Let's say like we play it in this way. Okay, this is not like who's winning, who's losing.
Okay, if he pays $1 and I match 3,
So if he puts $1, right, you can only match it. You can either match it or you can take it.
if I match it by the same amount of money,
You can only match it with the same amount of money. You cannot match it with 3 or whatever.
You get 1.5 and I get minus.
No, you got 1.
You get.
He got 2.5 and I got 2, right?
No,
Yeah.
you get
The
the
net
same.
is
I mean, yeah.
I see. So if I choose to not to match, he will probably just put 1 each time. I can get less in my case.
Yeah. Yeah.
That's the trick of the game, right?
Yeah. Basically, right? So you basically you get +2, or this is 1.5, or you can just take away his. You get a +1 right here. I mean, this is when you match the amount. This is when you just take off Sean's amount, right? So this is +2 if you match it. Otherwise, how much do you get? 3, right? If you just take away. So what would you do? What would?
I don't know.
No, would you
Maybe
choose
$1.
0, 1, 3?
$1.
You'll choose $1, right? So what would you do?
I just match.
Right. Right. So you won't choose $3?
I don't think so.
Well, why would you not choose
He may
$3?
just take $3.
Right. Exactly. So
If it's a sequential game, we can build the trust.
there's no trust here. That's what you cannot do. You cannot do collaboration. That's basically you cannot talk to each other. It's just you're there on your own. You're a separate entity and he's
But
separate.
if it is a sequential game, every time he put 3, I match. So by that, he knows I will match every time. So he will earn more by putting 3.
Yeah, I know that, but this is not about collaboration because there are instances where there cannot be
There's
collaboration.
no memory, right? Between each.
There is memory. Yeah.
If there's memory, I know each time he will match $3. I will start put $3 or something.
But how do you know he'll match $3?
I can try.
He can just run
several
away,
times.
Yeah.
Yeah, I can try. Maybe.
No, his payoffs. I mean, just look at the payoffs, right? His payoffs here. What did we do right here? We just looked at like the payoffs. How much is going? That's why we said defect is a dominant strategy, right? So there's no collaboration here. It's all about payoffs. Do you get that?
Yeah, but well, just in case I don't collaborate with him, I can still get more if I choose to match in the long run.
Which one? This one?
Yeah,
How you get?
because if I don't match, he will choose 0 or 1 each time. So maximum I can get 1 in that case.
So that is continued relationship, right?
Yeah.
That is when you do when you commit to a long relationship. But this is like that's different. I mean that's another game by itself. But this is like
You can mention that, Siddhardth. I guess like the whole thing is like this is not continuing game, like you just playing once and.
yeah.
So
Okay,
there's
I have
no memory between each.
I mean memory is there when you think about the game, as a single game. But when you think about the commitment thing, right? No, by memory what do you mean?
I mean, I cannot remember what's the last.
But he wants to find the
They only
pattern.
play
He wants
once.
to.
Play once.
So you play
Yeah.
Play
on.
once.
So each
You
game
play only
you
one?
play only 1 round.
Yeah.
So-
You either match.
So it's
you
not
need to
sequential.
really just say it at the beginning.
Okay. Okay.
Then how do you define sequential then?
The sequential
Sequential
game
is-
is not the same as in game theory. Doesn't mean that they play many times.
Then what's the
Sequential game is just like what is described now is like everyone take turns sequentially, but the game still
You
can finish.
move first,
For example,
right?
you have
After that
like
I move.
4 players, you can or 2 players, you can 1 play and then 2 play and 1 play to play finish. But it's not like okay, yeah. Or you can play it infinitely. But this one, he didn't mention. Actually, he should have mentioned right at the beginning. We're only going to play it once. And actually, it's better to also describe the whole game before you show the
Right,
outcome.
right.
Yeah.
Are you gonna look for something else or?
No, this we're going to experiment.
Okay, please. Yeah. There's something.
So this is more like let's say this is player A, right? Sean. Okay, so he basically has he can choose between 0, 1, and he can choose between 3, right? So these are his 3 different strategies that he can choose, right? So if he chooses 0, I mean, right there the game is over, right? I mean, he cannot do anything if he chooses 0. So the payoff is basically 0, 0. Okay, and if you choose 1, right? Bay could either match it or not match it, right? I mean, he could either match it or take it. So if he matches it, right, Sean will actually get a payoff of 1, right? And Bay would get a payoff of
1.5?
1.5, right? So so when he doesn't when he puts in 1 and Bay doesn't match it, right? So Sean would get -1 and Bay would get like
Take the money.
okay. So and this one is the same match, so right. So
3 and 2 and -3 and 3.
right. So this is basically how sequential games are shown in the form of a tree. Okay, and so this is pretty this is kind of self-explanatory. So when you try to analyze a game using a tree, right? It's more like so this was basically the strategy that Sean was using. He was trying to explain. So if Bay, right, if he were to give him $3, right, $3 in the thing, he would have a better payoff, just running away with the $3 rather than trying to match it. In which case, Sean would have got a +3 and a 2, and Bay would have got a 2, because this is basically a higher payoff than this one, right? So he basically tried this particular thing, but they would have done much better, right, if somehow they could have got to this point, right? So this is basically a classic example of a lender borrower, like an investment firm game, where Sean is basically say the lender, okay, and Bay is more like some startup trying to put in funds for his firm, right? So, but this particular model, right, doesn't really work, because you would want basically you would want to invest more money. Even for Bay, it would have been really nice if you invested more money, right, in the particular game, so that he could also try more stuff with it. So this is if you change this particular payoffs, right? So to benefit if you just take off, let's say, your profits from 1.3, 3 plus 3 to plus 1.9 and 3.1, right? Let's say you change this particular incentives. You just give more incentives to Bay, right? Rather than this is the previous payoffs. These are the new payoffs, right? So if you give more into this, the game by itself would basically converge into this particular solution, right? Which is preferential for both, because when you try to match it with the $1 thing, you also get a lot more payoffs, a lot more value here. And Bay also, instead of choosing this particular strategy, he would go in for this particular strategy, right? Because you basically get more payoffs here. So this is basically what they call as incentive design, and in normal, in more realistic scenarios, what they do is they try to put in minus. So this is more like when you try to run away with the money, it's more like you're not he's like a lender and you don't pay him back, right? It's more like in a realistic scenario, it's more like that. But when you try to put in some sort of an asset here and here, your base payoffs is much lower here, right? When you compare it with this, so there's a lot more possibility that he'll try to work for the money he's got, and try to either converge here or try to converge here.
Okay, I have a question. This game is the one game that repeats sometimes, or
this is the whole game by itself.
Must continue. For example, maybe Sean 10 times play and Bailey 10 times play, or it's a 10 times play between two pairs.
Okay, so this particular game that we consider right now is just once. This is the whole game. The relationship ends here. Okay, but there are games where there is a longer relationship, right? So you try to. So there is basically what they call a trust factor right there, right? So let's say so Sean and Bay, right? They basically they say that for the next 10 years they're going to work with each other, right? So at that time is the trust factor, right? You need not show really high payoffs at the beginning. You need to show some sort of trust, which is basically some sort of a payoff, right, in the initial thing. But just to make sure that the relationship is long, right? But this is just once. We consider just this particular game to be one, and just played once, and the relationship ends there.
So, okay, to my understanding, so Bailey's not playing against Schwan. Is that the concept? They're not playing against one another? Okay, and so Bailey seems like he's gonna win all the time. It's just that it's a matter of better choice that he wants to make, so he would maximize that profit. But why, if this is a one-time thing, like I would always try to not match a one and take his one, or like,
Yeah, but you get a better payoff here, right?
Yeah, but it's a one-time deal.
I know what you're getting at. You just want.
I just want some money. I guess even it's one time, probably you still choose 1.5.
No, but he's saying that it's just free money and you just take it.
Like, okay, here's other, like Bailey sees what Schwang selected, like if Schwang selected.
Yeah, so he basically, he's right here.
Okay.
So he knows what. Yeah. So okay, so this is basically like just regular jargon in sequential games. This is known as like the decision node. So in whichever node you tend to try to decide between strategies, right? So this is basically the decision node, and these are the edges of the node, and this could basically be called a path. Yeah. So this might be used like
Also, if I'm in Schwang's place, I wouldn't even play this game.
Huh?
I won't put any money in it.
So yeah, these are called the end nodes,
So
the ones that come last. So we did that,
Because you
and
can even extend this tree to a multiple round game by extending the leaf nodes.
sure, yeah.
So
By extending the end nodes, right?
you're not going to mention backward industrial?
Yeah,
The current
right now, yeah. So there was another thing that needs to be looked at here, right? So there is a very simple way of calculating the actual solution of this particular game, right? So let's just we can actually find the solution of this particular game by just observing the payoffs at the end. Okay, so let's say that Sean really wants to find out what kind of choices would be the best solution, the most realistic solution for the game, right? So he would first step into Bay's shoes. He'll see what if Bay, right? If I don't match, right? What will Bay basically do at this particular decision, right? I mean, at this particular junction, and then he would notice what Bay would do right here, and right here also, right? So Bay would basically get 0 here, right? So if Sean chooses 0, Bay would basically get 0 again, and Bay would get 1.5 and 1 if Bay chooses to match the amount or not match the amount, right? So Bay would normally go with 1.5, right? And Bay would basically get 2, 3 here. So he would prefer not match the amount right here, right? So mostly if this is the only choice he makes, I mean the solution is pretty evident, right? So it's basically 0, 0, right? So if he chooses 1, if Sean chooses 1, right? So it's basically Bay would always choose 1.5. So the solution here is 1.5, right? And if he chooses 3, this would basically be the payoff that they get, right? So, which according to from these, Sean would basically choose this particular thing, right? Because that gives him the best payoff, from 0, 1, and -3. So this would be the solution for the game. And this particular method of stepping into other shoes, seeing, trying to work out the game backwards is called backward induction. Right? So.
Why you didn't choose 3 and 2? Which one? Yeah, this one.
Yeah, exactly. So he didn't choose 3 and 2, right? Because Bay right here could get a better payoff choosing 3,
Oh, yeah.
right? So this particular thing is gone.
This is called
Backward induction.
backward induction.
We look at another example. Let's say there are two armies, right? The Saxon army and I don't know, I think it's the Norwegian army or something. So let's call it the Sax army and the N army. Okay? So they basically have to choose between fight and running away. Right? Retreat. Run away. So the N army here, after observing this particular move, they choose their option. So this is basically what happens. So if the let's just call it the S army. So if the S army basically tries to like if it fights and the N army fights again, right? Like looks at that decision, fights again. Both get a payoff of 0,0, right? And if S army fights and the N army runs away, right?
Then the S army gets 1 and the army gets 2.
It's good to run away.
Yeah. I think it's the other way around.
Yeah,
Sorry.
What's that kind of weapon that does this?
Is this example interesting? I don't know. Like just simple.
Do you want me to just go on then?
Yeah, I think you can skip this kind of example. It's trivial.
Okay. So let's try to look at the Stackelberg model. So before going into the Stackelberg model, we'll just look a bit into the Carnot model, right? See, so the Carnot model basically has two firms as players. And their strategies are the quantities they produce. And the cost of production is basically CQ. So where C is the marginal cost and Q is the quantity produced. So the whole cost of production is basically the marginal cost into the quantity.
What's the relation between strategies and quantities?
So strategies are basically how much, let's say there are two competing firms, right? Coke and Pepsi, for example. So the strategies are basically how much of quantity they need to produce, right? And the cost of production is basically CQI, right? The marginal cost into the quantities. So let's assume the price to vary by the function A minus B, Q1 plus Q2, where Q1 is quantity of company 1 and this is quantity of company 2, right? So the payoffs are basically like, revenue minus cost. And this is basically the revenue is,
The P is the price.
P is the price.
So
Yeah.
the two forms has the same.
The price of, yeah. So,
They use the same form.
yeah. So the payoffs are basically the revenue minus cost, right? The amount of profits they make. That's the payoffs. So this is basically like, the revenues are the price, the amount of revenue here. Minus CQ1. So the price into the quantity they produce minus the cost of production, right? So like when you try to, and they would basically try to maximize their particular profits. Let's say we consider company 1, right? It's basically maximize according to their, maximize their profits. With respect to Q1, so and working out the math, you basically like get the so if you maximize this particular profits with respect to Q1 and you equate it to 0, right? You get like the optimal value, like Q1 start is basically, Q1 cap is basically.
I mean, I understand what you're talking about, but
Take the first out the directive.
Yeah.
but don't point it that way.
It's not
Okay.
gonna
Okay. But basically at the we are looking at simultaneous games right now. We are not looking at a sequential game, right? So at simultaneous games, basically Q1 cap is equal to Q2 cap. The optimal value is here, right? Because basically at Nash equilibrium, right, they are in best response to each other, which basically says like the optimal values need to be equal to each other. So this is so you can Q cap is and you get the optimal value to be by 3p. So this is basically the Kondo model. I mean, this is basically to find out the optimal quantities for the Kondo model, where you're looking at simultaneous choices between the two players, and you find out the optimal quantity that would be produced here.
So for different companies, they have different C. I mean, C is different for different.
In this particular model, we look at identical products. So, which is basically, like everything's the same. But if there are different models like the linear city model and all that, which look at differentiated products. So that's a different model. We look at the most simple cases.
Excuse me, what's A and B?
It's just some parameter which the price depends on. I mean, it just goes out by this particular function. It doesn't have. I'm not sure if it really has any. Sorry. So now we look at the same model in terms of sequential games, the topic that we are discussing about. So let's say that like if Q1 basically increases, right? In this particular model, if Q1 increases,
The price of Q1 or the
the quantity increases, right? So the best response of 2 of Q1. So this is basically the best response of company 2 for Q1. Like, you know, after observing Q1, right, the best response for this particular thing would basically decrease, right? And so basically, like, you know, if you're firm 1, right, you'd basically try to produce like more in order for the best response to come down, right?
If you produce more, well, if your opponent produce more, if you produce less,
Right.
you can sell less, so you can earn less.
Yes.
But, okay.
That's basically your profits come down, right? So if the other firm produces more and you produce less, right? I mean, that induces you to produce less, right? So this is basically how it varies, right? This is this particular thing. Q2, and this is the price. So if you produce, it's yeah, I think this is VR2 of Q1. So this is the other firm's best response according to that particular equation, right? If this is where the Nash equilibrium is. So if you were to produce more, right, this would basically, how do I say that? Yeah, so if Q1 were to produce more, right, on this particular graph, you basically see that Q2 goes slow when Q1 produces more. Do you see that? Huh? Okay, so when Q1 produces, when Q1's quantity increases, right? So basically, let's consider this Q1 quantity, this particular curve, right? When Q1 basically increases, Q2 decreases, right?
Okay, the total amount of the Q1 and Q2 is fixed.
Where?
The total quantity of Q1 plus Q2.
Actually, the slope is supposed to be lesser than -1. So the rate of change of Q2, right, is much higher than the rate of change of Q1. The Q1 plus Q2 actually increases. It's not fixed, but the rate of change of Q2 is much higher than the rate of change of Q1.
I'm not sure what you're talking about now. But you have solved the equations there, right? You already say that if Q2 increases, the optimum Q1 response will be.
No, but that would confuse with Q1 and Q2. Q1 plus Q2 to be a constant.
If I know like Q2, like the other guys, what is going to produce, that will be my best response already. Right? So if I have sequential gain, then I will just exactly do that. Like Q1 hat is equal to whatever you have written down there.
Sorry.
That one.
This one.
Yeah.
Okay.
If you know Q2, that's exactly my response, right? That's my best response, right?
Okay. No, but still he was asking if Q1 plus Q2 is constant, right? In in the Stackelberg model, it's not a constant.
It's not a constant, but then afterward you remember something that I'm not sure like what you're talking about. But let me go back.
Okay. Maybe I have like notes for that. So we come back to this, right? So basically the central idea of the Stackelberg model is we try to use backward induction, right, to solve for like a sequential game of sequential view of the Econo model. So for backward induction, right? Let's say that or in the stackle bus, right? You basically, if you're player 1, right, you put yourself in player 2's shoes, and you try to solve for, like what player 2 would actually conceive that particular quantity to be, right? So it's basically like, from our Econo model, we basically get that A minus C by 2B minus Q1 by 2. So this is like, like if Q1 were to be known, right? Q2 would basically follow this particular equation. But so taking this value and trying to see what Q1's response, what player 1's response would be for this particular value, is basically like this particular value. So this is, you try to put in the payoffs here, the revenue minus cost thing, and you basically try to substitute Q1 taken as a value, right? Where Q2 is basically given to be this. You try to put it in here. You try to maximize it with respect to Q1, and then find the optimal value of Q1. I'm making a small mistake here.
See that one question?
Yeah.
If Q1 and Q2 both increase the number of products, the price of total value is less than.
Okay. So
based on this, P is equal to A something fixed minus B multiple the total quantity of product 1 and product 2 is if both companies increase the number, the price will be less.
Yes, because consumer surplus will be more, right? The prices will go down, but profits of firm 1 will go up.
When both companies increase the number of plus Q1, Q2, the profit of company 1 will go up,
Yeah.
or both?
When both increase their quantities, when both increase their quantities, the prices will come down, and we cannot say about the profits, right?
So because the increase of price probably is not as much as like increase of the
Right. So, but if Q1 were to increase the quantity, like right here, right, and this will basically induce Q2 to decrease their quantities produced.
So that the total quantity is equal to the minus C over 3B.
Total quantities is basically Q1 plus Q2.
So it's
Right.
fixed, right? They try to make sure the maximum profit. Otherwise, if both companies increase the quantity, the profit of both companies goes down.
Another question. This price is priced for one product or the price of all of the products?
It's just one product.
For example, this P is, for example, if you want to find, for example, what is the benefit of the one company is equal to P multiple the number of the quantities, for example, P Q1 it's the income of the company.
Yeah, I mean that's just one product we deal about here, right? I mean, why do you think?
It's my question that this P is the total income of the company or the price of one quantity of the
total income, the total, I mean, whatever the quantity that's right here. So, you know, like, it's basically the income of the, yeah, the income of, income of quantity Q produced. You can say it to be that, right? So, you were asking something? No, I didn't explain this really well, but the quantities, like you were saying, right, it's not fixed, right?
Excuse me, something I said, what was the difference if it was not just income, it was just for one? Yeah, this one.
No, it's just, you know, it's just the Q is basically.
No, I mean that if the problem was not just for the income, it just was just one product. What's the solution?
No, it can be one, it can be anything. It's just Q, it's just a.
It doesn't matter?
Yeah, it doesn't really matter, right? I mean, why do you think it matters?
But if the total quantity equal to that, those quantity equal to the cost of the equals the price.
So, well, I don't think I explained this too well. Anyway, so let's. So we now go into like the information sets. So before, right, we were looking at games with.
You override that? Okay, I guess it's better to just explain this
Again?
rather than, yes, I mean rather than like
Okay.
go to another.
So let me. So basically let's just start from the first again, right? P is basically A minus B, Q1 plus Q2, right? So the cost of production is basically here CQI or C. Let's just consider use of one CQ1, and the payoffs are basically revenue minus cost, right? So the revenues are the price of each item. Minus B, Q1 plus Q2 into the quantity produced by Q1, right? Of one, let's say. The price into the quantity plus minus the cost. The cost is CQ1. Okay. So here we then maximize this particular equation.
excuse me, is it U1, Q1, Q2?
Yeah, basically Q1, Q2. This particular function. Maximize this particular equation, and you basically get Q1 cap is equal to A minus C
Over 2B.
over 2B, right? Minus Q2 by 2, I guess, right?
I guess like it's even good to really go through the algebra.
Oh, really?
Yeah, although it's obvious.
Okay. So. Yeah. I mean, I just differentiated this, equated it to 0.
So differentiate Q1, right?
Yeah.
A, the first term.
Yeah. A multiple Q1.
Okay. So difference
No, missing one term here. There's a Q1 inside also, right? Did you?
No.
They have two big.
Oh, okay, you already okay.
Yeah. This is basically yeah. Right. So this is our equation, and so at the Nash equilibrium, right? Q1 cap is basically equal to Q2 cap. Right? Basically, they are trying to be the best response of each other, right? So let's just put this quantity as
I don't think it's a good argument that you say it's really hand waving.
so I mean, in more we can actually say that like if you were to move away from the equilibrium, right? I mean, it's basically the best response argument again, right? You would like how we saw in the prisoner's dilemma.
You can say it's because of symmetry, but it's not because of less equilibrium. I don't think so.
It's because of Nash. Why do you think it's because of
It
symmetry?
doesn't really have much to do with when you say it's best response of the others. Therefore, like the two has to be equal. If you don't have symmetry of the problem, then you don't basically have Q1 pad, you don't have Q2 pad. Now it's equal just because the problem is symmetric. For example, if like you have like different payoff for the two guys, then generally it doesn't have Q1 pad is equal to Q2 pad.
So what would
For
you?
example, if your payoff.
Yeah, I mean
for one
I know
of
what
the
you're
guys
saying,
is-
but
yeah.
what do you think like would be?
It's because of the problem is symmetric, but even that you want to, it's a little bit hand wavy, but you shouldn't say it's because less equilibrium, because that's nothing to do with that. You cannot say it's best response of this or that, therefore these two to be the same. It doesn't. Let's say I have the payoff if one of the guy like can charge a little bit more, I have a different constant, like one of the guy has a different constant than the other, then apparently you don't have these two will be the same. So it doesn't matter whether this is like treating this is the best response of the other guy, and therefore you say like these two are the same.
So you are saying if they are using different field
It's just
structure.
it's just because now the problem is symmetric, and now we are kind of cheating in the sense because we know it's symmetric, therefore we expect the solution is the same. But it's not really
Why the problem is symmetric?
symmetric in the sense that like both payers are basically getting the same payoff for what they for example, like if
You
for
mean
those-
A, B, C for component 1 and component 2 is equal.
Yes. Yeah. if not symmetric, it's something like company one looking at a little bit different, like pricing. For example, his cost is a little bit higher than company two, for example. Then apparently you won't have like Q1 hat equal to Q2 hat, right?
So how would you define that then? Like, how would you?
That's what I'm saying, right? You cannot hand wave and say it's flash equilibrium. It has nothing to do with flash equilibrium and the best response. If you have pair one, for example, like the cost for pair one is a little bit higher. Like you have cost is like instead of C you have like C1 and like pair two have like C is equal to C2. Then I can assume you like Q1 hat will be equal to Q2 hat, right? So it has nothing to do with flash response, nothing to do with flash equilibrium. It's only because the problem is symmetric. Therefore, we cannot expect that the Q1 hat is equal to Q2 hat for a non-sequential game. Because like both of them now, they have the same amount of information. Both of them to know like who the other side is, what is the other side's strategy.
But so we're looking at we're looking at the Nash equilibrium right now. Right? At that particular point.
But do you agree with me that?
Yeah,
exactly right. So you cannot use that argument saying, okay, let's response of this and that, therefore like blah blah blah, therefore like this. Yeah, there's nothing to do with that. To say to conclude that Q1 hat equal to Q2 hat.
Well, if you have a different fitness function, you will still end up in some point where you don't want to move up. The point probably is not like this equal to that, but there is some point.
But now you're jumping ahead and claiming that Q1 hat equal to Q2 hat. And what I listened right now that like the argument is saying something like best response of this and that and then that's good. But that is not the reason that writing Q1 hat equal to Q2 hat, right?
Yeah.
That's the thing I want to
totally agree.
emphasize.
Well, okay. So
Okay. Continue.
Okay, and one question: if A, B, C for each company was different, what is the, for example, the quantity of Q hats, Q1 hats and Q2 hats?
Exactly. You cannot jump into that. Then we need to maybe he'll try to solve the sequential game first, and then like we can go back. Maybe offline. Yeah.
okay. So we look at this right now. So we'll try to compute the same thing for a sequential game here. The sequential game, let's just start from here, right? So let's say you're player one.
So one question. So this Q is the optimum total number of product you are going to produce.
Yeah.
It's not saying it's a fixed number, but this is best number.
Yeah. So let's say you're player one, and in a sequential game, right? You basically look at player two's choice, right? Player two, how much he would produce, and according to that, you try to produce it according to his response, like how we saw in that particular graphical thing. So in a sequential game, we see that Q2 would basically, the optimal value would be A minus C over 2B minus Q1 by 2, right? It's the same thing like you were saying, it's symmetric, right? And we basically try to take this value to be Q2, right? And then we try to plug it into our particular equation here, and then maximize with respect to Q1 and find the optimal value of Q1. Something
I'm
wrong?
thinking like is that one is when you set Q1 hat equal to Q2 hat, I guess we get a solution A minus C over B instead of over B.
Okay,
No, over 3.
I think
Over 3B?
Yeah.
Q2
Oh
over
yeah,
4B,
3B,
right?
yeah, over 3B.
Over 3.
4B.
3B.
4B, right?
3B is right.
Over 3B. C over 3.
Minus Q, let's say, 2,
Yeah, it's
oh, Yeah, A minus C over 3. This right here. Okay, so we get Q2's the optimal value here, and we try to plug it in like, in this particular equation in with respect to, in place of Q2 there, and we try to basically do the same thing. Yeah. Please do correct me if I'm wrong.
Plus Q1 V.
Plus this one? Oh, okay. Yeah. And this is basically try to differentiate this. Is it right? Is it right? So this is basically so this is basically yeah, so in the sequential game, this is basically the optimal value for Q1, A minus C over 2B. want me to go to
Yeah.
with this done with
Get to be that's nice.
so do you want me to go to information strength?
No, I guess you better just okay. Can you give some physical meaning here? I don't see like you actually give a lot of insight right now.
So physical, like let's try comparing this to the Carnot quantity, right? Can we do that? So in the Carnot quantity, it's basically like Q1 would be producing A minus C over 3B, right? The optimal value. The Carnot quantity, we see that in this particular thing, I mean in the Stackelberg model, in the sequential games, right? The quantity of 1 basically increases, right? Yeah. So its profits basically increase, right? So this is basically like like the well, this could be termed as a first mover advantage. The Stackelberg model could be termed as a first mover advantage. And also another thing that I wanted to point out was like when you consider like the total quantity produced, right, in the Carnot model and the Stackelberg model, we actually let's try to the total quantity is basically yeah. So 3 and this is A minus C by okay. So we've got Q1 here. Let's try to compute Q2. Q2 from here is. Now I'm just trying to compute the total quantities in the Stackelberg and the Carnot model. No, yeah, it's basically the same as 4B. C over 4B, yeah. Right, A minus C. You see how I got like you're able to see how I got Q2, right? I just substituted in this particular equation. Right? We got Q1 here, we substituted it right here, so we got Q2. And so we see that when we compare these two, we see that the overall Q1 plus Q2 has risen up here. When compared to the Carnot model, and what else can we? What else do you think we could find?
So the one is really bigger. I don't know.
Yeah,
Okay.
Stackelberg is bigger than Carnot. I mean the total distance. We also see that the profits of firm 1 goes up, and yeah, basically the profits of firm 2 come down.
Excuse me, I think I lost the track. And what's the difference
I know.
between C and S?
C is basically the Carnot, the one that we
The
talked.
Carnot is bigger, right? 1/2 plus 1/4.
This is 3/4. That's 2/3, right?
Yeah, but it's like 2/3. It's like 3/4. Oh, okay.
Okay, what's the difference between C and S?
C is basically the Carnot model, the simultaneous game that we were looking at. S is the Stackelberg model, the second model that we were looking at. I mean the sequential game. So in the Carnot model, we found out the Q1, Q2, like in the first part of the game, A minus A over 3B, right? The optimal quantity. In the Stackelberg, we made use of the backward induction, and we found out Q2 first. What would be the optimal value of Q2, and basically try to substitute it in for Q1. I mean, to find out the payoff function of Q1.
So the physical meaning is in first case is two companies starting at the same time. In the
Right.
first model,
Right.
the second model is one company start first,
Yeah.
and then another company joins.
Right. That's the. I mean, yeah, that's the physical. I mean, the thing that needs to be taken from here is how these particular results coordinate with the Stackelberg and the Carnot thing, what actually happens here.
Since in this part we have just 2 players,
Yeah.
always we have 2 players, or we can just add.
I mean, for the ones that we discussed, we have 2 players, but there can be more players also.
And if we have more than 2 players, the equation will change.
Yes. I mean, it depends on the obviously the equations would change. It depends on their payoffs and the total quantity and all that. So it would change. It depends on
Yeah, I mean that for the more than 2 players, is again 2 by 2 players, or no? We just consider for all of the players together.
Oh, so we don't consider each 2 players. So we just we expand the payoff matrix to accommodate 3 players. Or
You mean
4.
that we mentioned about the 1 player? Yeah, consider about all of the players.
Yeah. So for example, let's just say there are 3 players. Okay. So A, B, C, right? And each have 2 strategies. Let's say, right? So you would basically consider, let's say A takes the first strategy. You would try to compute the payoff matrix for A, right? And A takes the second strategy. You'll compute the payoff matrix for B, and then so basically they'll have their own payoffs. There'll be 3 payoffs. Let's say 0, 0, 0, 1, 1, 1, something like that. And then you'll try to compute the Nash equilibrium between those. But there'll be it will be the same thing. So this is how you would basically compute
It doesn't
it.
matter, 2 players or more than.